This is section 4.4. It's called the fundamental theorem of calculus. So previously, if I gave you a definite integral and I said to find the definite integral of x from 0 to 2, we would do it geometrically. So I know that this means we look at the function x, and we're going to look at this graph from 0 to 2, and this is what this represents, the area of that shaded region. So I'm just going to do it geometrically. It's a triangle, 1/2, base is 2, the height is also 2, so this integral, definite integral, has a value of 2. Now we want to be able to do this without necessarily doing it geometrically or drawing a picture every single time and using an area formula. So what we're going to use is what's called the fundamental theorem of calculus, and what this says is if you have a definite integral, the way that you evaluate it algebraically is you take the antiderivative, so the antiderivative little f is big F, plug in the upper bound and subtract off the lower bound. Okay, so let's try it with this example here. So this definite integral, the antiderivative of x is x squared over 2, and I'm going to start with this. This is notation saying I'm going to plug in the 2 and plug in the 0. So if I plug in 2, I get 4 over 2, which is 2, minus, plug in the 0, 0 squared over 2 is 0, so this is 2. So exact same thing they got out here. So this is just another way to do this problem. So let's try another example both ways. So if I give you this, it may be, some problems it may be easier just to do it geometrically. So I know this means we're looking at the function 3. I'm looking at the graph from 0 to 4, so it's the area of this region, which is really 4 times 3. So this is 12. If you're going to use the fundamental theorem, this says that, okay, the antiderivative of 3 is 3x. Plug in the upper bound, which is 4, so I get 12. Subtract off what you get when you plug in the lower bound, which is 0. So my answer is 12. Exact same answer when I do it geometrically. Okay, let's try a couple more examples where we want to do it using the fundamental theorem without necessarily graphing it. So let's look at, let's try a trig one. So 0 to pi fourth of secant squared x dx. Okay, so the antiderivative of secant squared is tangent of x. So there's my antiderivative. So I'm going to plug in the upper bound, so tangent of pi fourths. Subtract off the lower bound, which is tangent of 0. This is 1. This is 0, so this value is 1. Okay. Let's try this one. Negative 2 to 3 of 6x squared minus 5 dx. Okay, so first thing, take the antiderivative. So the antiderivative of 6x squared is going to be 6x cubed over 3 minus 5x. And I'm going to plug in my bounds. I would probably just clean this up to be 2x cubed first before I plug in my bounds. So I'm going to plug in the 3 here and here. So if I do that, I get 2 times 27 minus 15. And then you're going to subtract off what you get when you plug in negative 2 into everything. So that would be 2 times negative 8. This is going to become a plus 10 here. And if you punch this all out, do the arithmetic, you'll get to 45. Okay. Lastly, let's take a look at one absolute value function. So let's say I give you this. For absolute value functions, the easiest way to do it is to do it geometrically. So if there are some problems, instead of using the fundamental theorem, it's easier to do it geometrically. So this one, the easiest way to do it is just sketch the graph. So I know the vertex is 1/2. There's my v. I'm looking at for the area under this graph from 0 to, let's say this is 2 over here. So this represents this area. Okay, I'm going to go ahead and just find the area of the two triangles and do it geometrically. So this one here, it's 1/2. Base of the triangle is 1/2. The height of this triangle, if I plug in 0, is 1. So the area of the little triangle is 1/4. Then I'm going to do this one. It looks like the base of the triangle is 3/2. The height of this triangle, if I plug in 2, it looks like it is 3. So this is 9/4. So if I add them together, I get 10/4, which is the same as 5/2. So that would be the value of this definite integral. Now, if you're going to do this algebraically, which you can, remember with absolute value, you have to think about the two cases. So the place where it splits into your two separate lines is at 1/2. So you're going to have to split it up into two separate integrals. So you're going to have to go from 0 to 1/2. And if you plug in any number from 0 to 1/2, this is going to be the opposite scenario. So you would have the opposite of 2x minus 1 dx. That would give you this area here. Then you're going to have to find this piece separately, and we're going to go from 1/2 to 2. And if you plug in any number between 1/2 and 2 here, this is the positive scenario. So this is what you would have to do. So if you wanted to do this using the fundamental theorem, you would do this. You would break it up into 2 separate integrals. Then you can do the antiderivative, plug in the bounds, and do the arithmetic, and you would get the same answer. But I think this is a much longer way to do it.